Hello. Today's discussion is all about sensitivity analysis in linear programming. Sensitivity analysis, or the post-optimality analysis, is used to determine how the optimal solution is affected by changes within specific ranges, specifically in the objective function coefficients and in the right-hand side, or the RHS values. Sensitivity analysis is important to a manager who must operate in a dynamic environment with imprecise estimates of the coefficients. Sensitivity analysis allows a manager to ask certain what-if questions about the problem. So we proceed with graphical sensitivity analysis. LP problems, or the linear programming problems, with two decision variables, graphical solution methods can be used to perform sensitivity analysis on the objective function coefficients and on the right-hand side values for the constraints. For example, given this LP formulation, maximum equals 5x sub 1 plus x sub 2. So our constraints are x sub 1 must be less than or equal to 6. Another one, it's 2x sub 1 plus 3x sub 2 must be less than or equal to 19. X sub 1 plus x sub 2 must be less than or equal to 8. So x sub 1 and x sub 2 should be greater than or equal to 0. By solving the LP formulation, we have now the given graphical solution. This line here represents the first constraint, which is x is equal to or less than or equal to 6. It is in a straight line. It's because we don't have given values for the x sub 2. And then this line here, that is the graphical solution for the second constraint, which is the 2x sub 1 plus 3x sub 2 less than or equal to 19. And then the last line we have here, that is the graphical solution for the third constraint, which is the x sub 1 plus the x sub 2 is less than or equal to 8. How about this line? This line here represents the graphical solution of our objective function, which is the maximum 5x sub 1 plus 7x sub 2. But we could observe here that we have here our optimal solution, which is x sub 1 is equal to 5 and the x sub 2 is equal to 3. The objective function coefficient. Let us consider how changes in the objective function coefficients might affect the optimal solution. The range of optimality for each coefficient provides the range of values over which the current solution will remain optimal. Managers should focus on those objective coefficients that have a narrow range of optimality and coefficients near the endpoints of the range. If you could recall, this is the graphical solution of our LP formulation. We have there the objective function line. That is the line for the 5x sub 1 plus 7x sub 2. The range of optimality. Graphically, the limits of a range of optimality are found by changing the slope of the objective function line within the limits of slopes of the binding constraints line. The slope of an objective function line, which is max c sub 1 x sub 1 plus c2 x sub 2 is equal to negative c1 divided by c2. And the slope of a constraint is a sub 1 x sub 1 plus a sub 2 x sub 2 is equal to b is negative a sub 1 all over 2. Let's take a look with this example. the range of optimality for C sub 1. Okay, given the first constraint, which is x sub 1 plus x sub 2 is equal to 8, we need to get for the slope using this formula, that is negative C1 all over C2. So for this constraint, since it's just x sub 1 and x sub 2, we have their numerical value, which is 1. So to get our constraint here, that would be negative 1, which is the x sub 1, all over x sub 2, or that is 1. So negative 1 over 1, or simply negative 1. So for our first constraint, the slope will be negative 1. And then for the second constraint, we get again the numerical value for the x sub 1, which is 2, we have here, negative 2. And then the numerical value for the 3 x sub 2, that would be 3. And then you put there 3. Negative 2 over 3 is the slope of our second constraint. So after getting the slope of the constraints, we need to find the range of values for C sub 1 with C sub 2 staying at 7. So if we could recall, our objective function is max is equal to 5 x sub 1 plus 7 x sub 2. So we will retain the value of 7 x sub 2, or the C sub 2, such that the objective function line lies between that of the two binding constraints. So negative 1 we have here is less than or equal to the slope of our objective function, which is negative C sub 1 all over 7, is again less than or equal to negative 2 over 3. So we have already here the values. So we need to multiply this one by negative 7 in order to cancel 7 under the denominator. So that would be negative 1 times 7, and then negative C sub 1 over 7 times 7, and then negative 2 over 3 times negative 7. Oops, I forgot there. Negative 7 and negative 7. So this one, it's negative 7 times negative 1 will come up with 7, which is here. So negative times negative, that would be positive. And then since we would be able to cancel 7 here. So positive C sub 1 is already here. That would become positive C sub 1. And then negative 7 times negative 2, that is 14 here, all over 3. So we have it, the range of optimality for C sub 1, that would be 14 over 3, or simply, if we're going to compute that, 14 over 3, or simply 4.67, is less than or equal to C sub 1, and the value of C sub 1 should also be lesser than or equal to 7. So this is the optimality ranges for C sub 1. We have 4.67 and 7. Okay, we have a question here. Would a change in C sub 1 from 5 to 7 with C sub 2 unchanged cause a change in the optimal solution? So the answer is, there is no. It's because C sub 1 is equal to 7, and the condition is 14 over 3 is less than or equal to C sub 1 and less than or equal to 7. So it still satisfies the optimal solution. Our next one is we are going to compute for the range of optimality for C2. Find the range of values for C2 with C1 staying at 5, such that objective function line slope lies between that of the two binding constraints. Okay, if you could recall, -1 is our slope for the first constraint, and the -2/3, that is the slope of our second constraint. And then the slope for our objective function, that is -5 all over C sub 2, since our formula for our slope is -C sub 1 all over C sub 2. So since C sub 1 is staying, so that is -5. So since we multiply this equation or these values with 1, the values changes, and at the same time, the logical expressions also change. Okay, so that would be 1 is greater than or equal to 5 all over C sub 2 is greater than or equal to 2 over 3. And then we need to invert this part. So if we're going to invert this part, all of the slopes also follows. So next one, it's we invert these values so that the C sub 2 will be on the top part, or it would fall under the numerator we have here. And then in order to cancel 5 as our numerator, we're going to multiply it by 5. So we have there 1 times 5 C sub 2 over 5 times 5, and then 3 over 2 times 5. So that would be 1 times 5, that is 5. So we cancel this 5, both 5, and then we'll remain it with C2 there. And 3 times 5, that would be 15 all over 2. So we have here. So our range of optimality for C2 is 5 is less than C2, and it is also C2 is also less than or equal to 15 all over 2, or that is simply 7.5. Again, we have a question. Would a change in C2 from 7 to 6 with C1 unchanged cause a change in the optimal solution? Again, the answer is no. That's because when C sub 2 is equal to 6, the condition 5 is less than or equal to C sub 2, and it's also less than or equal to 15 all over 2, or that is 7.5. So it is still satisfied. So we proceed with the simultaneous changes. The range of optimality for the objective function coefficients is only applicable for changes made to one coefficient at a time. All other coefficients are assumed to be fixed at their initial values. If two or more coefficients are changed simultaneously, further analysis is usually necessary. However, when solving two-variable problems graphically, the analysis is fairly easy. We simply compute for the slope of the objective function, which is -c x sub 1 all over c x sub 2 for the new coefficient values. If this ratio is greater than or equal the lower limit on the slope of the objective function and less than or equal the upper limit, then the changes made will not cause a change in the optimal solution. So we have here simultaneous changes in C sub 1 and C sub 2. Would simultaneously changing the values of C sub 1 from 5 to 7 and changing C sub 2 from 7 to 6 cause a change in the optimal solution. So if we're going to recall those values or the computed values before, when these changes individually, it did not cause the optimal solution to change. So let's recall that the objective function line slope must lie between that of the two binding constraints, which is -1 is less than or equal to negative, or the slope of our objective function, which is negative c sub 1 all over c sub 2, must be also less than or equal to negative 2 over 3. And the answer is yes. The optimal solution changes. It's because negative 7 over 6 does not already satisfy the above condition. It is already beyond the condition. Be sure that the slope for simultaneous changes in C1 and C2 must satisfy the ranges of optimality, or else the optimal solution will change. We proceed with the right-hand sides. Let us consider how a change in the right-hand side for a constraint might affect the feasible region and perhaps cause a change in the optimal solution. The change in the value of the optimal solution per unit increase in the right-hand side is called dual value. So later on, we will be able also to discuss what is a dual value. The range of feasibility is the range over which the dual value is applicable. As the right-hand side increases, other constraints will become binding and limit the change in the value of the objective function. So we have here dual value. So what is a dual value? Graphically, a dual value is determined by adding 1 to the right-hand side value in a question and then resolving for the optimal solution in terms of the same two binding constraints. The dual value is equal to the difference in the values of the objective functions between the new and the original problems. The dual value for a non-binding constraint is 0. A negative dual value indicates that the objective function will not improve if the right-hand side is increased. So we have here an example. Still using the LP formulation we have discussed as an example. So using the constraint 1, since x sub 1 is less than or equal to 6 is not a binding constraint. So the dual price, it will become 0. Change the right-hand side value of the second constraint to 20 and resolve for the optimal point determined by the two last constraints. Given the two constraints, which is 2x sub 1 plus 3x sub 2 is equal to 20. So the 20 there has been changed. And x sub 1 plus x sub 2 is equal to 8. So if you can recall our previous discussions, under the linear programming, we need to get the value of the x sub 1 and x sub 2 to get the optimal solution. Okay, given our two constraints, we're going to cancel one variable first, or in order to get or to compute the other variable. So for this example, I'm going to multiply the second equation with -2 in order for us to cancel 2x sub 1. So we have here 2x sub 1 plus 3x sub 2 is equal to 20. So -2 and x sub 1, that would be -2x sub 1. And we're going to multiply -2 with x sub 2, that would be -2x sub 2 is equal to -2 and 8, that would be -16. So we're going to cancel 2x sub 1 and negative 2x sub 1. So we'll come up with x sub 2 is equal to 4. Okay, we have already the value of our x sub 2, and then next one is we're going to get the value of the x sub 1 by using the value of our x sub 2. So I'll be using this formula, the second one. So that would be x sub 1 plus 4 is equal to 8, and x sub 1 is equal to 8 minus 4. So our x sub 1 is equal to 4. So the value of our x sub 1 is 4, and our x sub 2, oops, sorry, it should be x sub 2. Okay, using these two new values, we're going to get the value by substituting this with our objective function. So our objective function is 5x sub 1 plus 7x sub 2. So 5 times 4 plus 7 times 4 will come up with 20 plus 28. We're going to have 48 as the new value of our objective function. Okay, given the solution, which is you have here, the x sub 1 is 4 and the x sub 2 is 4, the value of new value for our objective function is 48. Hence, the dual price is equal to the z new value is equal minus z the old value. So our new value is 48. We're going to subtract it with 46. That will be 2. If you will be asking where did we get 46, so our original constraints are x sub 1 plus x sub 2 is equal to 8, and 2x sub 1 plus 3x sub 2 is 19. So we're going to multiply this one with negative 2. We'll come up with negative 2x sub 1, and then negative 2x sub 2 is equal to 8. And we copy the second one. So cancel x sub 2, negative 2 and 8, that would be, sorry, I had a mistake. Negative 2 and 8, that would be negative 16. So if we're going to subtract 19 with negative 16, that would be 3 equals 3. And then we substitute it, x sub 1 plus 3 is equal to 8. So the value of our x sub 1 will be 5. And then if we substitute it with our objective function, that is 5 times 5 plus 7 times 3. So that would be 25 plus 21, and then will be 46. So that is the value of our old objective function, which is 46. So if we're going to subtract these two, that would become 2. Okay, next one. We'll proceed with the constraint 3. The change in the right-hand side value of the third constraint to 9 and resolve the optimal point determined by the last two constraints. Or we're going to solve for the values of the x sub 1 and the x sub 2 just like what we did. Okay, I have here, to get the value of x sub 1 and x sub 2, again, I will multiply this, the second constraint, with negative 2. So we'll come up with 2x sub 1 plus 3x and negative 2x sub 1 and negative 2x sub 2 equals negative 18. Again, cancel. We have x sub 2 is equal to 1. So we have our x sub 2, the value of our x sub 2 is 1, and we're going to substitute it. So x sub 1 plus x sub 2 plus 9, x sub 1 plus 1 equals 9. So the value of our x is going to be 8 x sub 1. Again, using these two values, we'll substitute it with our objective function, that is 5 times 8 plus 7 times 1. So 5 times 8, that would be 40 plus 7. So our max value for this one would be 47. Okay. The solution we had is x sub 1 is equal to 8, and the value of our x sub 2 is equal to 1. And then our z, it's 47. The dual price is z new minus z old. So that would be 47 minus 46. For this one, it's using the original value of the constraint. So the value for the dual price is 1. The range of feasibility. The range of feasibility for a change in the right-hand side value is the range of values for this coefficient, in which the original dual values remains constant. Graphically, the range of feasibility is determined by finding the values of the right-hand side coefficient such that same two lines that determined the original optimal solution continue to determine the optimal solution for the problem. Okay, thank you very much, and these are my references. If you have questions, feel free to contact me.